let's think about what type of reaction might occur. If we have this molecule right over here, I won't go through the trouble of naming it. It would take up too much time in this video. But it's dissolved in methanol. It's dissolved in methanol. And we talk about what type of reactions. We're going to pick between Sn2, Sn1, E2, and E1 reactions. Now, maybe the first place to start, or the place I like to start, is to just look at the solvent itself. And when we're trying to decide what type of reaction will occur, the important thing to think about is the solvent protic or aprotic? And if you look at this solvent right here, this is methanol. It is protic. It is protic. And in case you don't remember what protic means, it means that there are protons flying around in the solvent, that they can kind of go loose and jump around from one molecule to another. And the reason why I know that methanol is protic is because you have hydrogen bonded to a very electronegative atom in oxygen. So every now and then in one of the methanol molecules, the oxygen can steal hydrogen's electron, and then the hydrogen itself, without the electron, the hydrogen proton, will be flying around because it doesn't have a neutron. So this is a protic solvent. Now, you might say, well, does anything with a hydrogen, would that be protic? And the answer is no. If you have a bunch of hydrogens bonded to just carbons, that is not protic. Carbon is not so electronegative that it could steal a hydrogen's electron and have the hydrogens floating around. So a big giveaway is hydrogen bonded to a very electronegative atom like oxygen. So this is protic. And when we think about protic, out of all the reactions we studied, that favors, so this makes us, well, even a better way to think about it is it disfavors. So it tells us that it's unlikely to have an Sn2 or an E2 reaction. And the logic there is an Sn2 reaction needs a strong nucleophile. An E2 reaction needs a strong base. Now, if you have protons flying around, the nucleophile or the base is likely to react with the proton. So it would not be likely to react with the substrate itself. So protic solution, you're unlikely to have an Sn2 or E2. What you are likely to have is an Sn1 or an E1 reaction. Both of these need the leaving group to leave on its own. And actually having protons around might help to stabilize the leaving group to some degree. So it makes Sn2, E2 unlikely, Sn1, E1 a little more likely. So far, these are good candidates. Now, the next thing to think about is to just look at the leaving group itself, or see if there is even a leaving group. And over here, everything we see on this molecule is either a carbon or hydrogen, except for this iodine right here. And we know that iodide is a good leaving group. So far, well, a good leaving group does not make it any less likely that you'd have Sn2 or E2. Both of those can do well with a good leaving group. But it's a necessary requirement for an Sn1 or an E1 reaction. Remember, an Sn1 and E1, in both of them, the first step is that the leaving group leaves on its own. That is the rate determining step. So that's a requirement for Sn1 or E1. So it still looks likely. We haven't seen anything that would make us think that we wouldn't have an Sn1 or E1. This is a good leaving group. Let me write here. Good leaving group. Now, the last thing we can think about right here is the carbon that we might be leaving from. So far, everything is pointing in the Sn1 and E1 direction. The final thing is, when this leaving group leaves, it's going to form a carbocation from the carbon that it's bonded to right now. And in order for that carbocation to be reasonably stable, at minimum it should be a secondary carbocation bonded to at least 2 carbons, but ideally it would be bonded to 3 carbons, be a tertiary carbon. Now, the carbon that the leaving group is bonded to, is a tertiary carbon. It's bonded to 1, 2, 3 carbons. So it is a tertiary carbon. So it can actually be a stable carbocation. It's a tertiary carbon, which once again favors Sn1 and E1. So all of the clues here tell us that Sn1 and E1 are going to happen. And actually, they'll both happen. So let's think about the mechanism. So in the very first step, the leaving group leaves in either one of these reactions. So if we look at the iodine, it already has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And in the first step, the rate determining step of the Sn1 or E1 reaction, The iodine is going to nab an electron off the carbon. I'll do that electron in green, right over there. That's going to get nabbed onto the iodine to make iodide, and then that carbon is going to lose an electron and become a carbocation. So after that very first step, we have something that looks like this. So that's our molecule. So you can, just so clear what we did, this arrow I'll do all the way over here. So it's clear that this is our next step. And what's happened here? Our tertiary carbon has lost its electron. So now this carbon right here has a positive charge. It's a tertiary carbocation. And now the iodine has become iodide. It has left the molecule. So it had its original 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. It nabbed one more electron from the carbon. And now it is, I wanted to do that in green. It nabbed one more electron from the carbon. Now it is the iodide anion. And the next, so this step right here is common to both Sn1 and E1 reaction. The leaving group has to leave. Now, after this, they start to diverge. And in Sn1, the leaving group essentially gets substituted with a weak nucleophile. And in E1, a weak base strips off one of the beta hydrogens and forms an alkene. So let's do them separately. So over here, I'm going to do the Sn1. And on the right-hand side, I will do the E1 reaction. So let me start over here. So the Sn1 is starting over here at this step. I'll just redo this step over here. So this has a positive charge. That has a positive charge here. The iodide has left. So the iodide has left. I don't have to draw all of its valence electrons anymore. And what's going to happen next? Well, we're going to get substituted with the weak base. And the weak base here is actually the methanol. The weak base here is the methanol. So let me draw some methanol here. So let me draw some methanol. It's got 2 unbonded pairs of electrons, and one of them, it's a weak base. It was willing to give an electron, but it has a partial negative charge over here, because oxygen is electronegative, but it doesn't have a full negative charge, so it's not a strong nucleophile. But it can donate an electron to this carbocation, and that's what is going to happen. It will donate an electron to this carbocation, and then after that happens, it will look like this. So that's our original molecule. Now this magenta electron has been donated to the carbocation. The other end of it is this blue electron right here on the oxygen. It is now bonded. That is our oxygen. Here's that other pair of electrons on that oxygen. And it is bonded to a hydrogen and a methyl group. And then the last step of this is another weak base might be able to come and nab off the hydrogen proton right there. Oh, I want to be very clear here. The oxygen was neutral. The methanol here is neutral. It is giving away an electron to the carbocation. The carbocation had a positive charge because it had lost it originally. Now it gets an electron back. It becomes neutral. The methanol, on the other hand, was neutral, gives away an electron. So now it now is positive. So now you might have another methanol. You might have another methanol molecule sitting out here someplace. That might also nab the proton off of this positive ion. So this one right here, it would nab it, or it would bond with it. It would give the electron to the hydrogen proton, really. The hydrogen's electron gets nabbed by the oxygen. And so then that becomes neutral. So then in the final step, it'll all look like this. We have that over here. The methanol that had originally bonded has lost its hydrogen. So it looks like this. We just have the oxygen and the CH3 there. CH3, it is now neutral because it gained an electron when that hydrogen proton was nabbed. So if you wanted to draw it, it has actually those 2 extra electrons just like that. And then if you want to draw this last methanol, it's now a positive cation. So it looks like this. So it's OH, CH3, H, and then it has unbonded pair right there. And now this has a positive charge. So that was the Sn1 reaction. Now the other reaction that's going to occur is the E1 reaction. So E1 reaction, once again, our first step, nope, I didn't want to do that. Our first step looks like that. So that is our first step. Let me get everything straight. So the leaving group had left. So they both, in each situation, the leaving group had left. Our iodide is up here. Our iodide is up here. And in an E1 reaction, you don't get substituted. What happens is one of the beta carbons gets a hydrogen swiped off of it by a weak base. Now let's think about what a beta carbon is. The alpha carbon is the carbocation carbon. That's right over there. That's the alpha carbon. Beta carbons are one carbon away. So this is a beta carbon, this is a beta carbon, and then that is a beta carbon. Now, this carbon over here is not bonded to any hydrogens. It's only bonded to other carbons. So that one cannot lose any hydrogens. And then we have to pick between this carbon that's bonded to 3 hydrogens and this carbon that's actually bonded to 2 hydrogens. I didn't draw it before, but it's implicitly there. It's bonded to 2 hydrogens. Now, Zaitsev's rule tells us that the dominating product is going to be produced when the carbon that has less hydrogens loses a hydrogen. So out of this, this carbon has 2 hydrogens, this one has 3. So the one that's going to lose the hydrogen to the base, or more likely to lose the hydrogen to the base, is the one that has 2 hydrogens, not 3, the fewer hydrogens. So our base in this case is once again the methanol, acted as a nucleophile in the Sn1, acted as a weak nucleophile in Sn1. Now it'll act as a weak base. So we have methanol right over here. That's a hydrogen. CH3 has some electrons right over here, has a partial negative charge. It will give one of the electrons to the hydrogen, just to the hydrogen proton. The hydrogen is not going to take its electron with it. That electron is then going to be given to the carbocation, to make it neutral, and it will form a double bond. So after that happens, we are left with something that looks like this. This was our original molecule. Now, this carbon right here, this carbon right over here in yellow, it has lost this hydrogen. This hydrogen back here is still there. I could draw it if I like. I don't need to. It just makes the thing messy. But it has now formed a double bond with the primary carbon. It has now formed a double bond. That electron that it had bonded with the hydrogen was now given to the carbocation that has a double bond with that. And then you have your methanol. Has now turned into a positive ion. It has now turned into a positive ion. CH3, and now it has this bond. It has this bond with the hydrogen. I'll even make that electron that it gave away in magenta. And then it has that extra lone pair of electrons. So in this circumstance, we looked at all of the clues. All of the clues were against Sn2 and E2. They favored Sn1, E1. So if you were to actually try to see what happens in this reaction, you would get products of both Sn1 and E1 reactions. These products and these products over here.